You know, every single time you log into a website, fill out a form, or even just look at a dashboard, you're talking to a hidden workhorse, a database. It's the engine in the background that stores and fetches information almost instantly, pretty much making our entire digital world work.
So in this explainer, we're going to pull back the curtain on this fundamental piece of tech. We'll get into what data actually is, how it's neatly organized inside of databases, and most importantly, why understanding all this is absolutely critical for anyone working in security and compliance.
We'll start with the real basics, what data is and how we classify it. Then we'll get into why databases are so much better than just simple files. After that, we'll take a look under the hood at how they're structured, and then we'll explore a really common and dangerous attack called SQL injection. And finally, we'll wrap up by covering the main types of databases you're likely to bump into.
So let's start at square one. What exactly is data? Well, to put it simply, it's any piece of information that's stored or processed by a computer. We're talking about everything from names and phone numbers to server logs and even passwords. It's basically the digital lifeblood of any organization today. Now, data isn't just static. It exists in one of three states. You've got data at rest, which is pretty much what it sounds like. It's just sitting on a hard drive or in a backup. Then there's data in transit, which is data actively moving across a network. And finally, data in use, meaning it's loaded into a computer's memory to be worked on. For anyone in GRC, this is huge. The core questions you have to ask, where is it stored, how is it moving, and who's processing it, they map perfectly to these three states.
Right, so it's a massive understatement to say that not all data is created equal. A public press release and, say, your company's secret financial plans obviously need very different levels of protection. And that's exactly where data classification comes in. It's the super important practice of sorting data by how sensitive it is so you can apply the right amount of security. A really common way to do this is with a 4-level system. At the bottom, you've got public data, things like marketing materials or job postings. Go up a level and you have internal data, stuff that shouldn't leave the company, like project plans. Now it starts getting serious with confidential data, things like financial results or employee PII. And right at the top is restricted data. This is the stuff where a leak would be a catastrophe. We're talking medical records or the company's private encryption keys.
So here's the crucial point. Just slapping a restricted label on a file doesn't actually do anything to protect it. An auditor isn't just looking for your policy document. They're looking for proof that you're actually enforcing it. Is that so-called restricted data actually encrypted? Are you logging every time someone tries to access it? A classification label is totally meaningless unless it's backed up by real technical security controls.
For a long time, we just stored data in simple files, like spreadsheets. But just try to imagine managing the HR records for 10,000 employees in one giant spreadsheet. It'd be a nightmare. It's slow, it's incredibly easy to corrupt, and there's no way to enforce any rules. It's basically like trying to run your company's most important archives out of a disorganized pile of folders on the floor. And that's where a database comes in. It's a system built specifically for storing and organizing data safely and efficiently. See, unlike a file on a shared drive that anyone can just open and mess with, a properly set up database enforces who can get in and what they can do. And it keeps a detailed audit trail of every single change. From a governance and compliance perspective, that is everything. So how do databases pull all this off? Well, let's take a look inside. The vast majority of databases organize data into tables, which honestly look a lot like really structured spreadsheets.
Okay, so each table has columns, and these define a specific type of information, like first_name or start_date. Then each row is one single complete record, like all the info for one employee. But the secret sauce here is something called constraints. These are rules that make sure the data is clean and consistent. For example, a constraint can ensure every employee ID is unique, or that a salary has to be a number, not text. It stops bad data from ever getting into the system in the first place.
But the real power comes from linking these tables together. You could have one table for all your employees and another table for all their training records. By linking them, you can ask really specific, complex questions and get answers back in milliseconds. That ability to instantly query across huge amounts of structured data is an absolute game changer.
So how do we ask these questions? We use a special language to talk with the database. But, and this is a huge but, if an application isn't careful about how it's built, an attacker can manipulate this language. and turn a simple login form into a very powerful weapon.
That language is called SQL, which stands for Structured Query Language. It's the standard way that applications talk to most databases. You can just think of it as a set of commands you give to the database, like, hey, get me this information, or update that record. It's actually designed to be pretty readable, almost like a sentence in English.
Okay, so let's look at a normal login. A user named Alice signs in, and the application builds a SQL query that looks something like this. It's basically asking the database, select all the information from the users table where the username is Alice and the password matches this password. Simple, clean, and it works. But here is where it gets dangerous. What if, instead of a normal name, an attacker types this very specific string of characters into the username field? A vulnerable application will just take that input and blindly stitch it directly into its SQL code.
And this is the result, a corrupted query. Let's break this down. That phrase, OR 1 equals 1, creates a condition that is always true. 1 always equals 1, right? This completely bypasses the username check. Then, those two little dashes, double slash, they tell the database to just ignore everything that comes after it on that line. So the entire password check is just commented out. It never even runs. The database sees a query that's always true, and it grants the attacker access without any valid credentials.
This attack is called SQL injection, and it's so common and so incredibly critical that it is consistently on the OWASP top 10 list of web application vulnerabilities. From a GRC perspective, finding a SQL injection flaw in any system that holds sensitive data is a massive red flag. We're talking serious regulatory consequences.
All right, databases come in a couple of different flavors. In most modern organizations, you're pretty much going to run into two main families of database technology.
On one side, you have relational databases, which are the kind we've mostly been talking about. They are all about rigid structure, tables and columns, and enforcing consistency. On the other side, you've got NoSQL databases. These were built for flexibility and speed. They can handle all sorts of data formats that change on the fly, which makes them perfect for really fast-moving applications.
But here's the key takeaway for governance. Despite all their technical differences, the fundamental GRC questions are exactly the same for both types. It doesn't matter if it's a rigid relational database or a flexible NoSQL one. We still need to know, where's the sensitive data, who has access to it, and is it properly encrypted and audited?
And that really brings us to the final question you should be asking yourself. Your organization's most critical assets, all that customer data, financial records, intellectual property, they all live inside databases. So, do you know which questions you need to ask to make sure they're actually safe?